right? Organic chemistry. So just make sure that you remind yourself of the chemistry of carbon. Okay? I think they're setting up for chemistry back there. So. Okay, and so most of the remaining 4% consists of these elements here: calcium, phosphorus, potassium, and sulfur. And again, when we talk about these macromolecules, we'll be seeing where these other elements come up in those molecules, okay, and what they do. And then, very interestingly, there's a number of trace elements that are actually required by an organism. And when we talk about trace elements that are required, they're typically required in very, very small quantities, but they're still essential to the organism. And those would be things like selenium, for example, or iron is another example. Okay, and I think this chart, yeah. So this chart basically shows these naturally occurring elements in the human body. Here's oxygen, carbon, hydrogen, and nitrogen, and their atomic numbers. Everybody remember what atomic number is? What's the atomic number? What does that mean? Number of protons, exactly, right? And that's the same, no matter if you have different isotopes of an element, the number of protons is always the same, right? Okay, the number of neutrons can change. So that's what that is. And then the percent of human body weight is over here. Elements making up about 4%. So as we said, these elements over here are found in smaller quantities, but they're there. Phosphorus, for example, is the atom that's linking together each of the components of a nucleic acid like RNA or DNA. So we'll be talking about the chemistry of phosphorus and phosphate a little bit in class. And then these trace elements down here make up a very small percent of human body weight. Does anybody know what do some of these things do? Why do we have to have them? Does anybody know? Why do we need iron? Anybody know that? Transport oxygen, exactly, right? So iron is an essential component of hemoglobin in our blood. If we don't have iron, or if we have an iron deficiency, then we have anemia, and we have a situation where our blood can't carry oxygen efficiently, and that can lead to problems. So it's a trace element, but we have to have it. And how about, anybody have any other ideas? Like what do some of these other trace elements do? What does manganese do, for example? Anybody know? Enzymes, okay? So when you think about trace elements, a lot of times what these are doing, actually, is they're helping enzymes to function. So in the case of manganese, there are some enzymes in our body, these mean proteins that are carrying out essential functions, catalyzing chemical reactions, where the chemistry of those enzymes requires an element like manganese to be present. If you don't have it, then the enzyme doesn't work, or it doesn't work very well, and then you have a problem. So a lot of these trace elements are there to ensure that enzymes in the body are working efficiently. Okay, yeah, question in the back. Yes, that's my next slide. Right? Yeah, so, no, right, exactly. So thank you for introducing that. So this is a slide that just shows a couple of effects of deficiencies of these kinds of trace elements. So as she's pointing out, if you have an iodine deficiency, it causes a disease called goiter. And it's very obvious in people that have a very profound iodine deficiency because they get an enlargement of their thyroid gland. Okay, and the reason for that, and I think we'll talk about this in a later lecture, the reason for that is that the thyroid hormone has iodine as an essential part of the hormone molecule. So if you don't have enough iodine, this thyroid gland has to work a lot harder to try to make enough of the, to try to compensate. And so it gets very, very large because it's really being stressed. Okay, so this is people that have goiter. So if you wonder why, when you go to the store and you buy a box of salt to use in cooking, you often see that the salt is iodized, right? Iodized salt. The reason is that we try to avoid iodine deficiencies in the diet by simply adding it in small amounts to sodium chloride that we buy at the store. Okay, and then over here, this is just showing you what happens in plants. So if plants have a nitrogen deficiency, now of course nitrogen is not a trace element, right? That's one of the common elements that we find in biological molecules. But if we have a deficiency of this in plants, you can see a very profound difference in the height and the quality of the leaves, how green they are in corn plants that have sufficient nitrogen and those that don't. Right? These are a lot smaller and they're a bit more yellow in color. So this is just again showing you that if you don't have enough of an element, then the plant is stressed. It can't make enough of the various molecules it needs to make to grow well, and so it shows those signs of stress. Okay, so let's talk a little bit about water. So water is basically the molecule that supports all of life. And one thing that I want to really stress, because sometimes we forget about this when we're in lecture and we're talking about macromolecules, talking about DNA structure, hormone structure, lipids, and things like that, is that the cells and the body, of course, is an aqueous environment, right? There's water everywhere. So whenever we're talking about macromolecules, you need to remember that these are surrounded by water, they're interacting with water, they're dissolved in water, and so water is really the medium of all of life. And so it's a biological solvent on Earth. All of the organisms require water more than any other substance. So humans can survive for multiple weeks without food. They can only survive for a few days without water. Right? They have to have water. It's really essential for all of the chemistry that's going on in our cells all the time. Cells are surrounded by water, and the cells themselves are actually 70 to 95% water. Okay, so again, everything that we're going to be discussing in terms of the chemistry of molecules that goes on in cells has to do with the way that they're interacting with water. And the abundance of water is the main reason that Earth is a habitable planet. So here's a great picture. You guys have all seen this of the blue planet, right? So the abundance of water on Earth is visible from space. There's a lot of water on this planet, and this is a unique feature that distinguishes our planet from others in the solar system and makes the Earth uniquely hospitable to life, we think. So how many people read about the Mars rover? Did you guys watch that thing coming down and landing on Mars? Did anybody see that? Yeah, right. It's really, really interesting, really cool. And so, you might have been, if you go to the NASA website, you can see pictures of the rover cruising around and the kinds of things that it's looking at. Well, one of the main things that it's trying to do, and you probably know this if you sort of have looked at the popular media about this, is trying to figure out if there's evidence for water on Mars. Now, I googled water on Mars last night, and I got 169, I think was it billion or trillion, anyway, entries, a lot of entries, okay? So water on Mars. So there's been a long history of people thinking about whether Mars might also be a habitable planet. Would it be a place where life could have evolved? And one of the ways that scientists try to answer that question is by looking for evidence of water on Mars. And so does anybody know, why is that? Why is that the critical thing to try to find if you wanted to ask, answer the question, could life have evolved on Mars? Could it exist on Mars? And there's not really one answer to this, by the way. Yeah. You can find life where there's water, okay? And do you know why? Why is water so important? We're going to talk about this, but yeah. Right, so it's necessary for chemical reactions that we know to be necessary for life. So, if you watch old Star Trek episodes and things like that, sometimes they try to imagine life forms evolving in different kinds of environments. But it's actually very hard, at least with all the chemistry that we know about that underlies life as we know it, very hard to imagine that actually going on without water as a solvent, okay? And we'll talk a little bit about why that is in a moment. But basically, there's lots of headlines like this. NASA finds water on Mars. And over the years, if you go back, it's not just with the Mars rover, it's with prior, probes that were sent to Mars and various kinds of spectroscopic studies that have been done, looking at what's going on Mars, what might have gone on in past history on Mars, has all really been directed towards this question. I think that scientists feel that if we had really good evidence for when and where there might have been water on Mars, we could get a sense of where we might find evidence of, if not current life on Mars, past life, right? Past life. Could there have been some kind of microbial life forms that evolved and then perhaps had to died off once the water disappeared? Okay, so something that I think is very, very interesting, very relevant to what we're reading about in the media. So let's think about this a little bit. So why is water so important, and why do we spend a little bit of time in Bio 1A thinking about the structure of water? And there's a few reasons for this. So first of all, water it's kind of an unusual molecule. It's what's called a polar molecule. That means that the opposite ends have opposite charges. Okay, so and I'll show you this on the next slide. And because of this polarity, it allows water molecules to form special kinds of bonds called hydrogen bonds with each other. Okay, and these hydrogen bonds are in certainly liquid water. They are constantly forming, breaking, and then reforming. Okay, they're forming, breaking, and reforming. I think the strength of a hydrogen bond is about something like 1/20th of the strength of a covalent bond. Okay, so they're weak bonds. They're weak chemical bonds. They're much weaker than a natural covalent bond, but they're very important. And as you'll see when we talk about the structure of big molecules like DNA and RNA and carbohydrates and other kinds of macromolecules, water and the ability to form these kinds of hydrogen bonding interactions is critical for the kinds of structures and functions that those big macromolecules have. So lest you think that, oh, well, hydrogen bonds are, they're weak bonds, so we don't really care about them. Actually, they're really, really important because there's lots of them, right? There's lots of them. So every time we think about a big macromolecule like a piece of DNA, that piece of DNA is actually surrounded by a large shell of water molecules that are hydrogen bonded to not only each other, but also to the actual atoms that are present in the DNA molecule, okay, forming a big hydration shell. And that affects the way the DNA molecule interacts with other molecules and the way it behaves inside the cell. So that's why I want to think a little bit about the way that these water molecules are put together. So you may remember from chemistry class that the orbitals around oxygen and hydrogen affect the way that these covalent bonds between the oxygen and each of the hydrogens in the water molecule are oriented, right? So water is not a linear molecule. It's actually a bent molecule like this. It's kind of bent. And there's another really important property of water that is important to think about, which is that, as we said, it's a polar molecule, polar. So what we mean by that is that the electronegativities of the oxygen and hydrogen atoms present in the water molecule are different. In other words, oxygen is a lot more electronegative than hydrogen. What that means is that negative charge tends to be focused on the oxygen molecule, whereas more positive charge tends to be focused on these hydrogens. And so you probably remember from chemistry class that we abbreviate that with a little delta negative to indicate more negative charge here, the electronegativity of the oxygen atom, which is red, and the delta plus on the hydrogen, indicating that more positive charge is here. So even though it's not an ionic bond, right? It's not as though the charge is completely separated, but nonetheless there's a polarity to the bond. And so that has the consequence, and because water is a bent molecule like this, it has an interesting consequence, which is that these hydrogen bonding interactions can occur very readily between adjacent water molecules, and also because of the angle of each of these molecules, you get this very nice arrangement of the molecules when they come together in solution or in a solid. And let's see if I can show you one more movie. I don't know if this has any sound. Can you see that? Right, so it's just an animation. This is an animation that's showing us, here are these water molecules. You can see the angle, and you can see how they're interacting through these hydrogen bonding interactions to form this really large network in solution. Right? And so water has this very interesting structure. And as I mentioned, these hydrogen bonds are constantly breaking and reforming with each other. And so that means that water is a great solvent, as you said. So we can dissolve things in it very easily because these hydrogen bonds can break with water and then they can reform with other things. And it also means that water has some very interesting properties that lend itself to function in biological systems. Now let's go back to my slideshow. Let's see. Okay, now I want to do another experiment, and I want to do an experiment with the eye clicker. How many people have an eye clicker? Okay, most people do. Okay, so if you don't have an eye clicker, don't panic, don't worry, because this is not going to count for any points. Okay, it's not going to count for any points. But I just want to make sure that we have the system. I have the system working that's working on my computer, and that we kind of go through a dry run to see how this is going to work in class in the future. Okay, so I'm going to show you the next slide. Okay, listen up, listen up. Okay, listen up. So the way this is going to work is what I want to do in right now and also in future classes is we'll talk about some things, and then I'm going to show you a question. And it might be it will be a multiple choice question, but it might be a question like this, or it might be a question where we have to think about it a little bit and maybe talk to your neighbors and try to think about the answer. And then we're going to vote, right? And you're going to vote with your eye clicker on what you think is the best answer to the question. And then we'll be able to look at what the results were for the class and get a sense of whether the material is making sense to you in general or it's not. So here's a question about water acting as a solvent. And again, this is a question that probably you may know the answer to from thinking back to your general chemistry class. And basically, the question is, which of the following best explains what happens when sodium chloride or table salt dissolves in water? Okay, so look at the possible answers here, and I'm going to start the timer, and I'm going to give you a minute to kind of think about it. Maybe you want to talk to your neighbors, and then we're going to vote. Okay, and I'll give you a heads up when we have just a few more seconds left to do the voting. Okay, so here's the timer. Folks, 10 more seconds. Okay, so did everybody get a chance to vote? Everybody get a chance to vote? Okay, so let's see if we can see what the results are. it's not showing it to you. Okay, so I'm going to figure out how to get that displayed. So basically, 3/4 of you, 76% of you, voted for C, the answer C. And that's the answer that I would have given, okay, which is that hydration shells are forming around the sodium and chloride ions when sodium chloride dissolves in water. And then most of the rest of you, another 20% of you, voted for B, which is that sodium and chloride ions are separating from one another. And that's true, but probably the best answer is really that the reason they're separating, the reason they can separate, is because they're actually forming hydrogen bonding interactions with water. And that's really what happens when something dissolves. And that's true for anything, right? Not just salt. It's true if we dissolve a molecule of DNA in water. It's true if we dissolve a protein sample in water, which we sometimes do in the research laboratory. In any case, that's what's happening, is that a hydration shell is forming around those molecules. Okay, so be sure to bring your iClicker next time because, wait, don't go yet. I have 2 more minutes, folks. Just stay where you are. So but I want to tell you that be sure to bring your iClicker next time because in class on Friday, we will be doing the iClicker as a graded problem. Okay, now I want to tell you a couple more things before you go. It's important. And this is in your book as well, but please be aware of this. So there's 4 essential properties of water that are really essential for life. And your book has a couple of nice discussions of all of this. So please have a look. But these are basically cohesive behavior, the fact that these hydrogen bonding interactions allow water molecules to stick together. So that allows things like plants to be able to draw nutrients up against gravity because water is a cohesive type of molecule. Water has a very important and unique ability to modulate temperature. It's why here in the Bay Area, we have a fairly mild environment. It's partly because we're here on the Bay. We have a lot of water that is able to easily absorb heat or release heat, and that tends to keep the temperature quite similar year round. Expansion upon freezing. So water has a very interesting property of being able to float. And if that were not true, then it would be very hard for life to survive during wintertime in areas where water freezes because the entire body of water would then freeze and there'd be no opportunity for life to carry on. But because ice floats, we have a situation where the ice will sit on the surface of a lake or an ocean and underneath is liquid water where life can carry on. Very important property of water. It's very unusual, right? Most compounds don't behave like that. And finally, as we just said, it's very versatile as a solvent, partly because of these hydrogen bonding types of interactions. So please review that in the book. Bring your iClicker on Friday, and we'll see you all in 2 days.